So far, we have been talking about cases where we know the genotypes of both parents. But what happens when that's not the case, when you don't know what genotype either mom or dad or both of them have? So let's hypothesize in the following example that we have a normal female, I know there's no such thing, who's married to a normal thing. I know there's definitely no such thing as a normal male. And the woman's brother is a hemophiliac. Okay, so neither the female nor her husband exhibit hemophilia, but the woman's brother does have the condition. And she wants to know what's the probability that her child is going to possess or exhibit hemophilia. So in situations like this, we draw pedigrees. Once again, squares for an unaffected male, we're going to give him a square with nothing in it. An unaffected female, a circle with nothing in it. An affected male, a square shaded in. Affected female, shaded in. Okay. And this is an example of the pedigree. This is the female right here, and she doesn't exhibit it, and we know she has a normal age because hemophilia is autosomal recessive, is a recessive trait, so she needs 2 copies of it. And here her husband doesn't have it, so he must have a normal X chromosome too. So it's on the sex chromosomes, not the autosomes. And he has a Y, which is normal. Then we'll know what the probability their child, son or daughter, we don't know yet, will have it. Well, the dad, we know the brother has it, so he has an X with a recessive H and a Y. The dad gave the son the Y, so he must have received the recessive H from mom. So we know that mom must be a carrier. Then we have the dad, and we know he's normal because he doesn't exhibit it. And he only has 1 H, and being homozygous, he'd exhibit it if he did. So we know she got the normal H from dad, and we don't know which of these 2 genes she inherited from mom. So how do we then proceed? So the first thing we do is we do a Punnett square for the daughter. The daughter could get X with a recessive H from the mother, or she could get a normal H from the mother as well. The father has to be normal because he doesn't exhibit the trait. The husband is also normal because he does not have the trait. And since the mother does not have the trait, she needs to be the carrier. So we do a Punnett square for the daughter. She can get the recessive or the dominant allele from her mother, and she can only get the normal dominant H from her father because he only has a Y allele, and he's not passing his Y allele on to his daughter. So we do the first possibility. This is dad, and this is mom, where mom has the recessive allele. So she could have this genotype, getting this allele from dad and this one from mom, or she could have this genotype, this allele from mom and this one from dad. Okay, these are the sons. Then she's not a son. To determine the Punnett square for her offspring, we cross one of her genetic combinations. Go back to the previous slide. We'll take this first one and then this one. So she could be either this or this. So there are 2 possibilities. We cross one of her genetic possibilities. This is the homozygous dominant with her husband's genotype. And we note that all 4 offspring are normal. None of them have hemophilia. None of them have hemophilia, and none of the 4 possibilities are carriers either. But we then cross the female's second genotype, okay, where she's a carrier with her husband's genotype. And then we note that 1 out of 4 offspring, her son right here, will have hemophilia, and 1 out of 4 will be carriers, this daughter right here. So does that mean 50% of all sons and 50% of all daughters will have hemophilia and or be carriers? No, that's not what it means at all. we base the total probability that the woman's offspring will have hemophilia on both Punnett squares, not one, but both, because we don't know which of her genotypes she actually has. The chance a child will have hemophilia is 1 out of 8. The chance a male child will have hemophilia is 1 out of 4, which is 25%. We can determine whether or not a trait is dominant or recessive by looking at the pedigree. Different pedigree patterns have different patterns of inheritance. For example, let's evaluate whether the following pedigree is dominant. We know if it's dominant, and we'll see the trait will be expressed. If it's recessive, the trait is not expressed, and we'll give it a little d. If the trait is dominant, then all individuals without the trait must be homozygous recessive. So here's the pedigree. We see 3 individuals with the trait. We give them a dominant D because they express it. This individual who does not exhibit the trait, we give 2 homozygous recessive alleles. Now we need to figure out what are the genotypes of the 3 other individuals in here. Well, mom and dad must have each given this daughter a little d, so they have to be heterozygous. This individual could either have homozygous dominant or a heterozygous genotype. So it is possible that this pedigree is in fact dominant. This trait is in fact dominant. Okay, so if the trait is dominant, the parents must both be heterozygous because their daughter does not have the trait. That means the male in generation 2 could be homozygous dominant or heterozygous. Since we can give each individual a genotype, the trait can be considered dominant. Let's look at the same pedigree, but now let's explore whether or not it could potentially be recessive. Remember, if any traits are exhibited, they must, and they're recessive, they need to be homozygous recessive for it. So each of these 3 individuals should have 2 of the same recessive alleles. Okay, both individuals in generation 1 and the male in generation 2 must have the genotype homozygous recessive R. The female in generation 2 must have at least 1 dominant R because she doesn't exhibit the trait. So this individual must have 1 dominant R because she doesn't exhibit the trait. So let's explore. Could this trait be recessive? Well, this son received 1 little R from mom, 1 from dad, so that could be. But where did this daughter get this dominant allele? Couldn't have gotten it from mom, couldn't have gotten it from dad. The only place is a possible mutation. So it's very unlikely that this trait is in fact recessive. So since we can't complete the genotypes, we can clearly state that no, that genotype, that trait is not recessive. If there are 2 affected parents and a non-affected child, generally we say the trait cannot be recessive. Let's look at another pedigree, and let's test something a little bit more complicated, but let's test it for dominance. Okay, so anyone that expresses it gets a capital D for dominance. Anyone that doesn't express it gets homozygous recessive Ds. Okay, because they're not expressing it. So let's see if we can fill in the genotypes. Okay, so this individual has a big D, so it must have gotten a little d from mom, and it could have gotten a big D from dad, so it could be heterozygous. This individual is homozygous recessive, could have gotten a little d from mom, but also must have received a little d from dad, so dad also has to be heterozygous. But then you have this daughter here who has a dominant allele, and both dad and mom have homozygous recessive, so there's no way that she could have received this dominant D from either mom or dad except by possible mutation. So this trait is clearly not dominant. Then we go to this same pedigree, okay, where we've just filled it in. Heterozygous, dominant, homozygous recessive, homozygous recessive, homozygous recessive, homozygous, and this one also must be homozygous recessive, but it expresses the trait, so it clearly can't be dominant. Now we want to do the same thing and test for recessiveness. So, if this is recessive, you need to have two recessive alleles, recessive alleles, recessive alleles. Anybody with a dominant, without the trait, must have a dominant allele. We see that this could have received one small d from dad, one small d from mom. You could fill that in. This one could have a small d from dad and a big D from mom. This one came from, we don't know who its parents are, but this individual could have received a small d from dad and a small d from mom, and this could be either way. So this could actually be a recessive trait. Now, one of the things I want to remind everybody is that it is possible to have a pedigree for a trait that can be both dominant or recessive. So sometimes when you're going through and you're testing it out, you'll see that it can be dominant, but go through again and see whether it can be recessive. And sometimes what you're going to find is that it can be both. That is, we can't distinguish it. Okay? For example, in generation 1, a female has a trait and the male does not. In generation 2, the male has the trait and the female doesn't, or both the male and the female have the trait. And then in generation 3, the male has the trait and female doesn't, or both male and female have the trait. Okay? And